Hello, this is Richard Hammock. Today I'm speaking on prime factoring bipartite graphs over the direct product. This is work I did with the graduate student Owen Puffenberger, and the paper will appear in the European Journal of Combinatorics this year. I'm going to start with a few definitions before we get to the statement of the theorem I'll be talking about. First of all, as I'm sure you know, a graph is bipartite if its vertices can be partitioned into two what we call partite sets. Let's call them B and W, in such a way that each edge of the graph runs from B to W. So you see B is the black vertices at the top, W is the white vertices at the bottom, and any edge of the graph runs between those two sets. Here is a more symmetric view of the exact same bipartite graph, again with its vertices colored black and white. And as you know, a graph is bipartite if and only if it has no odd cycles. I'm going to talk about two products today, the Cartesian product and the direct product. First of all, the Cartesian product is a way of multiplying two graphs, A and B. And the way you do it is you first of all take the Cartesian product of the vertex sets of A and B, and then for every fiber over a vertex of A, you put a copy of B. They're all there. And then for every fiber over a vertex of B, you put a copy of A. And you get the product, the Cartesian product of A and B. I'll call that A box B. Now for the direct product, it's a different type of product. And the way it's formed is, once again, you take the Cartesian product of the vertex sets of A and B, and anytime you have a edge running from a vertex A to B and A, and let's say 0 to 1 in B, you have an edge running from A0 to B1. If you do that for all the pairs of edges, all the edges in A and B, you get the direct product, which I'll call A times B. These graphs can have loops. If A has a loop, then we get, as you see, a isomorphic copy of B in the 5. It's commutative. A box B is isomorphic to B box A. It's associative. And also we have a distributive property. If B plus C represents the disjoint union of B and C, then A box B plus C is A box B, disjoint union A box C. And the exact same properties hold for the direct product. Notice that if we take a graph G and form G box K1, we get a copy of G. So G is always isomorphic to G box K1. Because of that, it makes sense to define a graph G to be prime with respect to the Cartesian product if whenever G is isomorphic to A box B, either A is isomorphic to G or B is isomorphic to G, and the other factor is K1. So it's the same definition we would use for integers, prime integers. We also have a notion of primeness for the direct product. Let's let K1 star denote K1 with a loop. And notice that in the direct product, G times K1 star is isomorphic to G. So K1 star is a unit for the direct product. G is isomorphic to G times K1. So consequently, we get a notion of primeness with respect to the direct product. G is prime with respect to the direct product if, whenever G is isomorphic to a product A times B, either A or B is isomorphic to G, and the other factor is K1 star. Now, the main theorem I'm going to discuss today involves prime factorization of the direct product, and we're going to see that whenever we have a prime factoring of the direct product of a graph, although it may not be a unique prime factoring, the bipartite factor is always unique over all prime factorings of graph G. Now, I'll state that a little more clearly later. we do have a few more definitions and ideas to get across before we get to that main theorem. One very major theorem due to Sabadusi and Vising in the early 60s is that connected graphs factor uniquely over the Cartesian product. So here's a graph G, and it's isomorphic to K2, box K2, box the 5 cycle. And Sabadusi and Vising's theorem states that for any connected graph, when you factor it into prime graphs, as is done here, each factor here is prime, that factoring is unique up to isomorphism of the factors and the order of the factors. We also have a notion of primeness, or prime factorization, for over the direct product, and this is due to McKinsey and Imrich. It happens that connected non-bipartite graphs factor uniquely into primes over the direct product. So here's a graph, and it's equal to this prime graph times that prime graph. And that factoring is unique, no matter how you factor this graph into primes. You'll get two factors. One of them will be this graph, and the other one will be that graph. It's unique. But here's an interesting fact. Prime factorization of connected bipartite graphs is not unique. For example, notice that we have C6 here, the 6th cycle, factoring as a triangle times K2. Here's another picture of the 6th cycle, and it factors into prime graphs, A prime times B, and clearly A prime is not the triangle that we had over here. So C6 factors in two different ways into primes, A times B and A prime times B. Here's another example. Look at this graph G here. It's A times B. And here's the same graph G that's another graph A prime times B. Now, G on the left is isomorphic to G on the right. If you interchange the green vertices and the red vertices on the right, you'll get the graph G on the left. So those two graphs are isomorphic, but they have different prime factorizations. Here's another example, a bipartite graph here, and it factors into this prime graph times that prime graph times K2. You may have to look at this for a while, but you can also see that it has a prime factoring with two factors. This graph turns out to be prime, and it times K2 gives you the original graph G. So this graph G factors in two different ways into primes, as A times B, and also as A prime times B. So different prime factorizations. And you even have, in this case, a different number of prime factors. So prime factorization of connected bipartite graphs is highly has exactly one bipartite factor. That certainly happened in A times B and A prime times B. B is the bipartite factor. On the left, in these two prime factorizations, K2 is the bipartite prime factor in those factorizations. It's interesting in these examples that the bipartite factor is the same, even though the factorizations are different. The same here. The bipartite factor is the path on 5 vertices here and here. In each of these two examples, the prime bipartite factor is the same. Now, for a long time, this was a conjecture that given any connected bipartite graph G, the bipartite factor in any prime factoring of G is unique. And the purpose of today's talk is to discuss a proof of that fact. The theorem is this. Given a connected bipartite graph G, the bipartite factor in any prime factoring of G is unique. Here's a picture illustrating that. Bipartite factors that differ. So we'll be proving that no matter how you factor a connected bipartite graph over the direct product, you get the same bipartite factor. Now, I'm going to issue a disclaimer just to make the discussion simpler. Today we're going to assume that for any two vertices x, y of our graphs, they satisfy that their neighborhoods are not the same. And such graphs are called R-thin graphs. It turns out the proof is a lot easier with this assumption. Everything we do today can be extended to arbitrary graphs, but the details are tricky, they're technical, and not very illuminating. So we'll ignore that. We'll just assume in the background that our graphs satisfy this, that distinct vertices have distinct neighborhoods. And having said that, I'm not going to say anything more about that assumption, but it's always lurking in the background. In my paper, this is dealt with very carefully to overcome this condition of R-thinness, but we're not going to worry about it today. Now, there are a couple of ingredients of our main proof. The first involves unique factorization over the Cartesian product, over box. Here's a theorem that we're going to use. Suppose G and H are connected graphs, and let's say they're isomorphic. There's an isomorphism phi from G to H. Then any such isomorphism has a structure that essentially looks like this. If you have an isomorphism from phi from G to H, and you prime factor G into prime factors over the Cartesian product and do the same for H, then the isomorphism will simply be an isomorphism on components that may permute the factors in some fashion. Essentially, phi would have a structure like phi of x1 through x5 is, say in this case, phi1 of x3, comma, another component function, phi2 of x2, then phi3 of x1, phi4 of x5, and phi5 of x4. So each component function is an isomorphism from one of the prime factors of G to one of the prime factors of H. Now, this theorem invites us to do something that's very useful. What we can do is, say, we could identify, in this picture, H3 with G1, which is isomorphic to, and so on. So we'll replace all the factors, or relabel all the prime factors of H with prime factors of G. And in that case, phi has an incredibly simple structure. Phi of x1 through x5 is just a permutation of the arguments of phi. It just scrambles them up. This is a very useful way of looking at isomorphisms between graphs that we'll take advantage of. Now, prime factoring over the Cartesian product is relatively simple. It's been known for a long time that the prime factoring is unique. It's not too hard to prove. Prime factoring over the direct product is much more complicated. So the second ingredient of our proof is going to be a way to link factorization over the Cartesian product, box, and the direct product. And I call this the Cartesian skeleton of a graph. It's the second ingredient of our proof. And the basic idea, our goal, is that we're going to create an operator S on graphs satisfying S of A times B is equal to S of A box S of B. It's sort of like a homomorphism between the direct product and the Cartesian product. So S of A will be another graph A that's related to A. S of B will be another graph that's related to B. And we call that the skeleton of B, and S of A is the skeleton of A, and S of A times B is the skeleton, or Cartesian skeleton, of A times B. Now, to motivate this, imagine that you sort of think of your graph as being a wall made up of bricks. The bricks are the vertices of the graph. And let's let n of x, which you think of as the neighborhood of x, denote the mortar around a brick x. So the neighborhood around a vertex x, or a brick, is its adjoining vertices. And imagine you want to know when two bricks x and y are at a diagonal in the wall, like this. So here's x and here's y, and they touch each other but at a corner. Is there an intrinsic way that we could identify that without really looking at the orientation of up or down, sort of like the product? We can, and the trick is to look at the neighborhood of x intersected with the neighborhood of y, this area right here. That you think about that maybe as a little intersection of mortar between the bricks. And x and y are at a diagonal, notice, if there's another brick z such that the neighborhood of x intersect the neighborhood of y is properly contained in the neighborhood of x intersect the neighborhood of z, which is this region here. And the neighborhood of x intersect the neighborhood of y is also properly contained in the neighborhood of y intersected with the neighborhood of z, that area. So given a brick z that has this property, that its intersections of its mortar with y and x properly contain the intersection of the mortar joining x and y, as in this picture, that would be an indication that x and y are at a diagonal. But this being a discrete world, it could be that nx intersect ny maybe consist of like one vertex, like one molecule of mortar. And in that case, you can't have these properties, but you could still have x and y at a diagonal. And for such a situation, they're at a diagonal if and only if you can find a third vertex or brick z with the property that the neighborhood of x is. Now, we're going to call any pair xy that meets one of these conditions diagonal. And notice this is not defined in terms of any orientation of right or left or up or down or any product. It's intrinsic to a graph. So the Cartesian skeleton of a graph G is defined this way. The vertex set of the Cartesian skeleton, S of G, is the vertex set of G. The edge set of the Cartesian skeleton of G consists of all pairs xy of vertices of G such that the neighborhood of x intersect the neighborhood of y is non-empty and xy is not diagonal. So I'll give you a picture of this, an example. Here's a graph A, a graph B, and their direct product A times B. And we're going to draw skeletons of each of these three graphs. Skeleton of A, the skeleton of B, and the skeleton of A times B. If you work it out, it turns out to be these red dotted lines. Down here we have the skeleton of A, here we have the skeleton of B in red, and over here in the product, the red dotted lines are the skeleton of A times B. And notice that in this picture, even though the skeleton was not defined in terms of any factoring, any orientation or sense of a diagonal or not diagonal, it nonetheless happens that, in this case at least, the skeleton of A times B equals the skeleton of A box the skeleton of B. You can see that happening if you ignore all the black and just look at the red. You get this property. S of A times B equals S of A box S of B. It turns out that this proposition is true in general. S of A times B equals S of A box S of B. And actually this is not just isomorphism, it's actual equality. These graphs on the right and left have exactly the same edge and vertex sets. They're identical. Here's a proposition. Suppose G is connected. Then, first of all, if G has an odd cycle, it turns out its Cartesian skeleton, S of G, is also connected. What about if G is bipartite? Well, in that case, S of G has exactly two components. Their respective vertex sets are the two partite sets of G. And you see that happening in this picture. Here's a graph G in black, and its Cartesian skeleton has two pieces, the part over here on one partite set of G, and the other part of the Cartesian skeleton is over here. Its vertex set is the other partite set of G. Now, furthermore, if you had an isomorphism from G to H, that is also going to be an isomorphism on the skeletons of G to the skeleton of H. Any isomorphism phi from G to H is also an isomorphism phi from SG to SH. And here, of course, we look at phi as being a map on vertex sets. That map on vertex sets phi is an isomorphism from both G to H, and simultaneously an isomorphism from S of G to S of H. Now, all of these things can be proved, but we'll just accept them as fact for this talk. Well, with these preliminary ingredients, we can now state the main theorem that we want to prove today. If a graph G factors as G equals A times B, and also G equals A prime times B prime, where B and B prime are prime and bipartite, then B is actually isomorphic to B prime. And I'm just going to give a sketch of the proof. The actual proof is very long. And here's what we'll do to prove our theorem. Let's suppose that A times B is isomorphic to A prime times B prime, that G is isomorphic to both A times B and A prime times B prime. And we're going to consider an isomorphism phi from A times B to A prime times B prime. Now, the first thing we're going to do with that is we're going to take the Cartesian skeleton of the image and the co-image. And by the theorem we cited on the previous slide, that phi is still an isomorphism from the skeleton S of A times B into the skeleton S of A prime times B prime. Now we're going to use that property of the Cartesian skeleton. Phi is now a map from S of A box S of B to S of A prime box S of B prime. In fact, it's an isomorphism between the two. Now remember that B and B prime are bipartite, so their skeletons consist of two copies of connected graphs. Let's call them B0 and B1 for B. So that's B right there, or S of B rather. It's B0 plus B1. And down here is S of B prime. It has two pieces. Call them B0 prime and B1 prime. So the plus is their disjoint union. So we've updated our map phi. Next, we're going to use the distributive property of the Cartesian product to distribute the S of A and the S of A prime into the parentheses. And we get a map phi that looks like this when we do that. Now, what phi is doing is, keep in mind that we have one component here and another component right there. So the skeleton consists of two disjoint copies, and the same for down at the bottom. So phi is really something that can be broken up into two isomorphisms on the respective components. On SA box B0, phi operates as, let's call it phi naught, as an isomorphism from SA box B0 into SA prime box B0. And on the other side, we get the other part of phi on the other component. Let's call it phi1. Now, bear in mind what's happening here. Remember that scheme we talked about earlier. Where did the direct product go? Remember that the edges of A times B, they run between the vertices of these two components of the skeleton. And the same for the edges of A prime times B prime. They run between the vertices of these two components of the skeleton of the lower graph. So phi naught is an isomorphism from this component of the skeleton to this component. Phi 1 is an isomorphism from this component of the skeleton of A times B to this component of the skeleton of A prime times B prime. But simultaneously, we're getting an isomorphism from A times B into A prime times B prime. So lurking in the background of everything we do from here on out is going to be this picture. The direct product is behind all the things we do, although we're quickly going to remove those edges again. But we'll always remember that the edges of A times B, they run between these components, and the edges of A prime times B prime, they run between these components. Now, the next thing we're going to do is notice that SA box B naught can be further factored over the Cartesian product. In fact, we could factor it into prime factors, and that's exactly what we're going to do. We'll do the same thing for S of A prime, for B naught prime. Basically, for all of these factors, we're going to further factor them into primes over the Cartesian product. So this diagram is going to be refined as follows. It looks like this. So remember, here's S of A, the skeleton of A. It's factored into prime factors over the Cartesian product. Our B naught is factored into prime factors over the Cartesian product. Here's SA again. Now remember, that's exactly what we had over here. It occurs twice in the diagram, and you see its prime factors. But B1, it didn't appear over here, so it has another prime factoring right there. And the same for the bottom. This is S of A prime, and it's prime factoring over the Cartesian product. And here's B naught prime, and its prime factorization over the Cartesian product. Here's SA prime again, and its prime factoring over the Cartesian product. And the prime factoring of B1 prime is right here. So phi naught is an isomorphism from this prime factoring over the Cartesian product to the one on the bottom. Phi 1 is an isomorphism from this prime factorization to this one. Now remember a few slides ago where we remarked that we can identify the factors on the bottom with the factors at the top in such a way that phi naught just permutes its arguments, and the same for phi 1. So with that in mind, we're going to look at some certain factors of prime factors in this diagram. And we're going to make things simpler, I'm going to divide them up into colors. I want to start off with what I would like to call blue factors. And the way blue factors work is they follow a certain pattern. If you take a factor F of the skeleton of A, phi naught is going to send it to an identical factor of SA prime. But remember that phi 1 inverse over on the other side, it's going to send factors back to S of A. And blue factors have the property that when you apply phi 1, and then, when you apply phi 1, let me start over again. Blue factors have the property that if you apply phi naught to them, and then phi 1 inverse, and then phi naught, and then phi 1 inverse, and then phi naught, and phi 1 inverse, and then phi naught, and phi 1 inverse, some even number of times you get back to where you started. It forms a cycle of factors. Let's call all of those factors blue factors. And they belong to, they're factors of SA and SA prime, as we can see here. Now, not every factor is going to be a blue factor, because you can imagine that maybe when you start iterating with this scheme, phi 1 inverse, phi 1 inverse, and so on, maybe you get a phi 1 inverse that's going to send one of these over to to B1, for instance. That didn't happen here. And once you get into B1 or B0, then if you're in B0, phi1 doesn't apply to that, and you terminate. So I want to now think about factors that they don't have quite the cyclic pattern. They terminate either in B0 and B0 prime, or B1 and B1 prime. And I'm going to call those factors green factors. And I'll show you what they look like. Green factors might look like this. You've got a factor, a prime factor of B0, and you apply phi0 to it, and it takes you down to SA prime. Then you apply phi1 inverse, then phi0, phi1 inverse, phi0, phi1 inverse, phi0, phi1 inverse, and then phi0, and you wind up in B0 prime. So notice that you started in and terminal points. Notice that whenever you have a green factor in B0, you get an identical green factor in B0 prime. Now you could also have green factors that start in B1, and they're such that if you apply phi1 and then phi0 inverse, and then phi1 and phi0 inverse, phi1, phi0 inverse, phi1, phi0 inverse, and then phi1, you finally terminate in B1 prime. So here we have a green factor in B1 that eventually took us to an identical green factor in B1 prime. So green factors have twins in B1 and B1 prime, as we see here. And remember, we also had twins. They appeared as twins in B0 and B0 prime over here. Now imagine that you now take the product of all green factors in B0, B0 prime, B1, and B1 prime. Just multiply them all together with the Cartesian product. Then their product in B0 is some graph, let's call P, and we have an identical graph down there, P. Both of those are products of green factors. Over here in B1, we have a product of green factors Q, and it has a twin product down here, Q, as well. Well, what other kinds of factors do we have? Well, it turns out we have factors that we might think of, I call them red factors. And a typical red factor might work like this. We start with a factor n of B0, let's say, and we apply that same scheme to it, but it might be that you don't wind up in B0 prime as you did for the green factor. It might work like this. Here's an n, a red factor in B0. You apply phi0, phi1 inverse, phi0, phi1 inverse, phi0, phi1 inverse, phi0, and you're right here. Now I'm going to jump over to the other copy of SA prime down there. So we're here. And then you apply phi1 inverse, and you wind up in B0. That's certainly a possibility. So with red factors, for every red factor you have in B0, there's a twin in B1. That's the way red factors work. And you can imagine that the same thing could happen here. I won't show you this, I won't have a slide for this, but you could have a red factor n here, or maybe call it m so it's not confusing. And it would have a twin over here in B1 prime. Now let's take all the products of red factors. Let's say the product of red factors in B0, it's called K. It's here, and you have a twin over there as a product of the identical factors that you had over on the left. And the same thing for downstairs. The product of red factors here, let's call that L, and you have an identical graph L over here. So we're looking now at products of red and green factors in S of the skeleton of B and the skeleton of B prime. Now let's think about what we have here. Remember, the skeleton of B, it was B0 plus B1. B0 plus B1. And we see here that that's K box P plus K box Q. k box p plus k box q. And we have an identical factor of k in each of these terms, which we can factor out over the Cartesian product. K times p plus q. The skeleton of B is k, it factors as k box p plus q. Now I'm going to omit the details here, but it's not hard to show that that factoring, k box p plus q, into red and green graphs, gives you a factoring of B over the direct product, k, which has two parts. It's not trivial. So this k has to be trivial. It's k1. B is prime, so k tilde is k1. Now, essentially, that means that the k here and here and the L, in other words, all the red factors, are all k1s. They don't even show up at all as factors. So the upshot of this is that there are no red factors. Only green factors in B naught and B1, and B naught prime and B1 prime. No red factors. So we're going to update our graph, our diagram a little bit, get rid of the red factors, and it looks like this. Now notice that our B, it has two partite sets, B naught, the vertex set of B naught and the vertex set of B1, and those are labeled by the vertices of P and Q. Now what about B prime, the other bipartite factor? It has partite sets who are the vertices of the component of the skeleton B naught prime and B1 prime, in other words P and Q. So we see here that the vertices of B and the vertices of Q, the vertices of B and the vertices of B prime under this identification are exactly the same. The vertices of B are the vertices of P and Q, and the vertices of B prime are the vertices of P and Q. I'm going to get rid of all the other factors in there. And notice now we have an identity map from B naught to B naught prime and from B1 to B1 prime. An identity map from the labeling of B up here to the labeling of B prime down here. And it turns out that that's exactly the isomorphism that we're looking for. Remember that the bipartite graph B, that prime factor, its edges run from B naught to B1 prime, from the vertices of P to the vertices of Q. B prime, the other prime bipartite factor, its edges run from the vertices of B naught prime to the vertices of B1 prime, in other words, from the vertices of P to the vertices of Q. And that identity map from B to B prime, the vertices of B to the vertices of B prime, that turns out to be an isomorphism. I'll skip the details, but this is just the gist of the proof. We can't hope to prove everything today, but this is the way the proof works. We get our desired isomorphism from B to B prime. And we're done. We've now shown how the theorem is proved. If a graph G factors as G equals A times B and G equals A prime times B, where B and B prime are prime and bipartite, then B is isomorphic to B prime. Thanks. I've enjoyed giving this presentation, and I look forward to discussing this over Skype. Have a great day. I hope you're enjoying the conference.